today we're going to be looking at section 6.1, and 6.1 is about measures of spread, specifically two measures of spread that we haven't talked about before, variance and standard deviation. We're going to look at how those two values depend on the mean of a set of data and how the calculations are a little bit different depending on whether we're looking at a sample with our data or whether we're looking at a population. So we've looked at measures of center, which are the mean, median, and sometimes the mode, previously in this chapter, and today we're going to look at measures of spread, or we're going to calculate values that tell us how spread out our data is. So we've learned how to find ways to talk about averages. We're going to now look at, can we describe with a number how spread out our data is? So we've seen some of these before with both the IQR and the range, and so now we're going to look at standard deviation and variance. So there's two ways that we can look at this, both population and sample. So when the data is a population, we use Greek letters for mean, variance, and standard deviation. The mean is labeled with this weird looking U. It's pronounced mu. Okay, it's like a U with a front tail on it. Variance is sigma squared. We've seen sigma before, but we looked at capital sigma. That's capital sigma. This is lowercase sigma. Sigma squared is the variance, and standard deviation is just sigma. And so variance is calculated from the squares of the deviations. Deviations are the differences between a value and the mean. So we're looking at how far away are each of our values in our data set from the mean. That's what variance is. It's the mean of the squared deviation. So population variance is the mean of the squared deviation. So we're going to find each deviation, square it, add them all together, and then divide by how many there are. Population standard deviation is a little bit different. It's the square root of the variance, of the population variance. Okay, so it's the square root of finding the deviation, squaring them, adding them all together, and dividing by how many there are. So once you have variance, it's really easy to find standard deviation. And so here's our equations to help us. So we've got sigma squared of the variance is equal to the sum of the squared deviations, or the sum from I to n of x sub I minus mu, all like squared each time, all over n, and then the standard deviation is the square root of all that. So why is standard deviation important? So we're going to calculate it here in just a second, but it's important for you to understand why we need to find it. And it shows how much variation or dispersion there is from the average or the mean. Low standard deviation indicates that the data points tend to be very close to the mean, okay, or they're compact, whereas a high standard deviation indicates that the data are spread out over a long range of values. For instance, in a manufacturing setting, you don't want a high standard deviation because you want all of your data as close to the mean so that when you're manufacturing different parts, they're all as similar as possible. It's impossible to make them all 100% identical, but you want your allowances either in the positive or the negative from your exact values to be as close together as possible so that things are going to work. So let's look at our example here. So we have a dot plot that shows the frequency distribution of the weights of the team members on the varsity wrestling team at a high school. And we want to find the variance and standard deviation for the weights of the team, treating them as they're the entire team. Okay, so we've got 4 120s, 3 135s, 3 145s, a 170, a 190, and a 285. Okay, so the first thing we got to do is we got to find the mean, or we got to find mu. So we're going to do 4 times 120 plus 3 times 135 plus 4 times 1 plus 3 times 145 plus 2 times 170 plus 190 plus 285. And that's going to be all over, we've got 10, 12, 13, 14. So when we calculate this out, we get that our mean is 152.5 pounds. So now what we have to do is figure out how far each point is from this mean. So we're going to do 120 minus 152.5. We're going to do 135 minus 152.5. 145 minus 152.5. 170 minus our mean, 190, and then 285. So we found all of the deviations by doing those subtractions, and so now because we're trying to find the variance, we need to square each of these. And then once we square them, we can add them up. So now I have all of my squared values. So now I'm going to weight them based on how many times they actually occur and then add them all together. So this 1056 occurs 4 times because it's from the 120. This one occurs 3 times, and 3 times, and 2 times, and then 1 time and 1 time. So I'm going to take each number and multiply it and then add it to the other weight values or the other deviations. Okay, so I'm taking 1056.25 times 4 plus, so I'm putting a little plus in here in between all of these, so that I'm adding up my deviations. Okay, so the sum of my deviations is 24,887.5, and now I need to divide that by my number of data points, which is 14. And so my variance, or my sigma squared, is 1,777.679. And so now my standard deviation, or just my sigma, is going to be the square root of that, which is 42.163. And we'll look more in other chapters about what we want to have happen with this variance and standard deviation. But right now we just need to practice finding them. So I got a variance of 1,777.679 and a standard deviation of 42.163. And that was when we treated the data that we have as a population. So let's talk about when data is a sample. Okay, so instead of using Greek letters, we use Roman letters. And so our mean is labeled as our x bar, and it's still calculated the same way as mu is, it's just a different letter. Our variance now is s squared, and our standard deviation is s. The only difference between population and sample is what we divide by. In a population, we divided by n. With standard deviation and variance, we divide by n minus 1. When these formulas were being developed, the statisticians that were doing it felt like dividing by n minus 1 created more accurate data than dividing by n, because we're looking at a smaller sample. So it's still the sum of the squared deviations, but instead of dividing by n, we divide by n minus 1. It's still the square root, again, just dividing by n minus 1. So this n minus 1, that's the big deal here. That's how it's different. So sample, n minus 1, population, n. So let's look at one more example, and then we'll be done for this video. And so now we're going to look at this wrestling team as if it were only a sample instead of a population. We still have the same mean, so x bar is still 152.5. If you need to look at that calculation, go back 2 slides or go back a little bit and you'll see it. So now we want to find the standard deviation and variance of this data. And again, we know the sum of the deviations, okay? The sum of the squared deviations, okay, is equal to 24,887.5. Okay, and so now to find variance, we're going to divide by not 14, but 13. And so our s squared is going to equal 1,914.423, and our standard deviation is going to be the square root of that, is 43.754. And by changing to n minus 1, we're taking into account the fact that not all of our data is represented. Okay, so the 1,914 is our variance, and our 43.754 is our standard deviation. So there you go. There's how we find variance and standard deviation. And just remember the difference between population and sample. Population we divide by n, sample we divide by n minus 1.